Um, Hi, everybody, and welcome back to the second part of my talk on the real spectrum compactification of the Hitchin component. So what we're going to do in this part of the talk, we're going to give a characterization of points in this compactification. We're going to, in order to do so, we need to define what are positive and F-Hitchin representations. And for understanding this characterization, we will use something that is called the Tarski-Seidenberg principle. And yeah, this is a really cool tool that we will see later, even in an application. So yeah, let's start. So we recall from the first part that the Hitchin component is a connected component of the character variety containing a very special representation, namely one of the form Yoda n composed rho, where Yoda n was the irreducible n-dimensional representation of PSL2R, and rho was in the Teichmüller space of our closed surface of genus at least 2. And now I want to give a useful characterization that in the form that I will state it is due to Fogg and Goncharov, that says that if you take a representation rho from the fundamental group of our surface into PSLN R, then rho is, its equivalence class is in the Hitchin component, if and only if rho is so-called R positive. And we will see on the next page what is the definition of R positive. But for now, let me tell you, this has some strong Anosov and positivity properties. And in particular, this allows us to prove that Hitchin representations are discrete, faithful, and diagonalizable. And we've seen this already for Teichmüller space, namely by definition, these were all discrete and faithful representations into PSL2R. And now we want to come to the real spectrum compactification, and I hope I convinced you in part 1 of this talk that in order to understand this compactification better, we need to look at representations into PSLN F, where F is some real closed field extension of R. So let me give you a definition. So a representation into PSLN F is called F-Hitchin if it lies in the F extension of the Hitchin component. And we will write hit Sn sub F. So let me explain what I mean. So this is a semi-algebraic subset of some R to the M. And what does F extension mean? F is an extension of R. So we can just consider the same equalities and inequalities that define the Hitchin component, but over F instead of R. And now you might wonder, okay, maybe there's probably not one way to define a semi-algebraic set, and that's correct. And this is a vector theorem that says that the F extension is independent of how the semi-algebraic set is defined. So the definition we gave here makes sense. And now comes the theorem that we all hoped for. So F is a real closed field extension of R. Rho is again a representation into PSLN F. Then rho is F-Hitchin. If and only if rho is F-positive. So if F is just R, then we get the same characterization back that we saw above, given by Fock and Goncharov. Okay, so now let me say something about what is F-positive. So let me define this notion. Okay, so we take HS to be a subset of the boundary of the universal cover of S. So S twiddle notes the universal cover S. So namely the set of fixed points of the fundamental group of our surface. And now we say a representation into PLSLF is F-positive if there exists a map M rho from the subset of fixed points into the full flags in Fn satisfying certain properties. So first thing I want to first say, full flags. So these are the full flags in Fn, so nested subspaces. And the difference between the dimension is always 1. And this can be identified with GL and F modulo the upper triangular matrices. So this might sound very complicated, but really think matrices. So we have a map from the fixed point set into these full flags that satisfy certain properties. So let me explain what these properties are. So first of all, if I take a non-trivial element gamma, then rho of gamma is diagonalizable with distinct eigenvalues, all of the same sign. The second property is that M rho is rho equivariant. So let me say what rho equivariant means. So that just means that if you act with an element gamma on a point x in the fixed point set, then this is nothing else than applying rho of gamma to M rho of x. So here we have gamma in the fundamental group and x in HS. The second property tells us that we want, if we take two distinct points, then we get a tuple of flags, M rho of x, M rho of y, and we want this tuple to be transverse. So what does it mean? If we take the ith dimensional subspace in our flag and the n minus ith dimensional subspace, then they should span the whole space. And these three properties, some of you might know, and these are the strong Anosov properties. And now we come to the positivity properties. So let me write this, positivity. If we take three distinct points, then we get a triplet of flags, and we want this triplet of flags to be positive. And I'm going to say in a moment what positive means, because it will come up again. If you take 4 distinct points on the boundary of the fundamental group in this fixed point set, in this order, so maybe look at this picture, because there you see the correct order, then the triplet of flags, where now I think here y and z are swapped, is positive. So you get a quadruple of flags, and this is positive. And these, so I'll give an example in a moment, but this just means that you have some rational or polynomial expressions that are associated to triples and quadruples of flags. And these polynomial expressions have to be positive. So let me give an example, because I think this is a lot to digest, but maybe we can go to the baby case. So if n is equal to 2 and our field are just the reals, then what we get, the full flags in R2, is nothing else than the choice of a one-dimensional subspace in R2. So you get RP1, which can be identified with S1. And a positive triple or quadruple is one that occurs in the correct order around the circle. And let me say, what are these? Maybe here, what are these polynomial expressions associated to triples and quadruples? In this special case, for the triples, if you know what that is, you can compute the Maslov index. And for the quadruples, this is given by the cross ratio. Okay, so this is the definition. This is maybe a lot to digest, but I now want to try to convince you of the forward direction of the theorem. So we need to prove that if we are F-Hitchin, so lie in the F extension of the Hitchin component, then we're F-positive. So we need to find this boundary map and check that all these properties hold. I now want you to convince you that property 0 holds. Okay, and proof idea for the forward direction is the Tarski-Seidenberg principle for the reals. The backwards direction uses the Bonner-Hondraya coordinates, but I don't think we'll have time to talk about it much at the end of this talk. But yeah, please come to the office hours and ask me if you want to know more about it. Okay, so what is the Tarski-Seidenberg principle? Let me give an informal statement first. So informal, it says nice statements hold over the reals if and only if they hold over a real closed field extension F. So maybe we can specify a bit what I mean by nice. So these are things or statements we can express using polynomials, equalities, inequalities, unions, intersections. So for those of you who know a bit, it's called the first order language of ordered fields. And this theorem allows us to conclude things to hold over F if we know they hold over the reals, even though we might not have the same tools. So over the reals, we can use continuity, we can use differentiability, and maybe all of this is not available over these real closed fields, different from R. So I don't know, they're not particularly nice. So this is a very, very powerful tool that allows us to transfer results we know over the reals to real closed extensions. And now let me give you the correct statement. So I'm going to formulate it again in the language of real algebraic geometry. If you need to catch up, go to watch the first talk for the definitions. So you take X in Rn+1, a semi-algebraic set, F again, a real closed extension of R, and pi, respectively pi f, will be the projections onto the first m coordinates. The first statement is that in fact pi of x So this is now a subset of R to the M is semi-algebraic. This might, I don't know, not be very surprising, but it's not too easy to see. And if you look at algebraic sets and you project them on coordinates, they're not going to be algebraic anymore. So this is very nice. And the second statement is that now, since X is semi-algebraic, we can look at it at its extension over F, and then we project. But this is nothing else than the projection, or we first project and then we extend. So this is now a subset of F to the M. This was again F extension. Okay, now we come to an application of the Tarski-Seidenberg principle, right? Like, what did I want to do? I wanted to prove to you, so this is the proof of the forward direction, which I call property 0. And yeah, let me recall that here. So we start with a representation in the F-Hitchin component. For a non-trivial element gamma in the fundamental group, rho of gamma is diagonalizable over F, and all the eigenvalues are distinct and of the same sign. So how can we conclude this using the Tarski-Seidenberg principle? So what are we going to do? Proof. We consider for a non-trivial element gamma in the fundamental group of S, a certain semi-algebraic set, which I call X gamma. So we're going to look at the set of all representations rho and vectors v1 up to vn and scalars lambda1 up to lambda n, such that rho is in the Hitchin component. VI's are going to be vectors. So these are going to be the eigenvectors of my representation, so of my element rho of gamma. So these are eigenvectors, so they have to be non-zero. Then I take my scalars. These are going to be the eigenvalues. And how do I express this property of saying VI is an eigenvector of rho of gamma to eigenvalue lambda I? I'm going to write rho of gamma VI is equal to lambda I VI for all I up from 1 up to n. Then I need to be a bit more careful, namely I want this VI actually to be a basis. So the determinant of V1 up to Vn, if I write them in a matrix, is non-zero. Now I also have another property. I want all the eigenvalues to be distinct and of the same sign. So I either have lambda 1 is bigger than up to lambda n is bigger than 0, or lambda 1 is smaller than up to lambda n is smaller than 0. And I claim that this is now a semi-algebraic subset of R to the m. So this is going to be for rho in the Hitchin component. So this is a semi-algebraic subset of R to the m times R to the n times n, right? I take n vectors in Rn, and then times, so we still need the scalars, which is another R to the n. So this is the lambda I in R. And this is semi-algebraic. Since the Hitchin component is semi-algebraic, the condition Vi is non-zero is a semi-algebraic condition. This is a polynomial condition. Here's a semi-algebraic, like an unequal is bigger or smaller, or is a union, and all of these are inequalities. So this is semi-algebraic. Okay, what is the next step? Now we're going to look at the projection onto the first M coordinates. Okay, so remember the first M coordinates were exactly where rho lies in the Hitchin component. So the projection onto the first M coordinates gives us a surjection onto the Hitchin component. So we have a map pi from X gamma onto the Hitchin component. And why is this a surjection? So this is just by the characterization of Fock and Goncharov, right? They said a Hitchin representation is R positive, so it satisfies all these properties. And now we will use the Tarski-Seidenberg principle to extend this set to F. So we will have that if we take the F, the extension of the projection of the F extension of X gamma, so we extend it to F. Then by the Tarski-Seidenberg principle, this is nothing else than we first look at the projection and then we extend to F. So this is Tarski-Seidenberg. But now this was surjective, this map pi, so this is just the F extension of the Hitchin component. So this is surjective pi, surjectivity of pi, exactly. So, but this means that F Hitchin representations have the same property. So they're diagonizable with distinct eigenvalues, because for every element in the F extension, we will find an element in this extended set X gamma, extended to F. And using what we've just proved, we can construct this limit map for F Hitchin representations that was called M rho. And we can prove that it satisfies 1 to 4 using the Tarski-Seidenberg principle again, and the characterization by Fock and Goncharov. So we know everything holds over R. We can express everything in this semi-algebraic way. And then Tarski-Seidenberg gives us for free that the same holds for F Hitchin representations. And this is the proof of the forward direction. And now let me spend the last 1-2 minutes for the other direction. So the backwards direction uses the Bona-Honjaya coordinates for the Hitchin component. They generalize the shearing coordinates for Teichmüller space that were introduced by Thurston, and they are associated to a maximal geodesic lamination on the surface S. I drew a picture below, and yeah, if you have questions about this or you want to learn more about it, please feel free to come to the office hours and ask me all the questions. Thanks so much for your attention. I hope you enjoyed it, and you enjoy the rest of the conference. Thank you.